So today I'm going to present our work on single-shot Romer EPTI on diffusion at Connectome 2. High B value diffusion MRI is valuable for microstructure imaging, but is often limited by low SNR. This requires longer scan time and limits spatial resolution. It can also be limited by dynamic distortion due to the strong eddy current. Our goal here is to address those limitations using single-shot diffusion Romer EPTI so that we can achieve distortion-free, high SNR microstructure imaging at high B values and high spatial resolution within a clinically practical scan time. We will demonstrate the efficient microstructure imaging at Connectome 2. In this study, we aim to leverage advanced acquisition technologies along with further developments to improve SNR, image fidelity, and resolution for microstructure DMRI. This includes SNR efficient and motion robust Romer acquisition, where we acquire distortion-free volumes with rotating encoding for high SNR efficiency that have thicker slices, and then combine those encoded orientations through motion-aware Romer reconstruction to recover high-resolution diffusion images. Here is an example showing the SNR gain provided by Romer acquisition at high B value of 5,000 compared to conventional SMS EPI. We leveraged the high performance gradient for high B imaging from the ultra high gradient performance scanner Connectome 2. The better gradient performance reduces TE at high B value for SNR gain. The shorter echo spacing can also help with improved G factor for further improved SNR. We leverage single-shot EPTI readout for in-plane encoding rather than a conventional EPI. The EPTI result is distortion-free by design because the encoding happens in KYTE space, therefore resolving distortion-free multi-echo images across the readout. This is important because it let us push to higher B values and higher resolution while preserving anatomy much better than the standard EPI. We also employ a variable density encoding, which is with higher sampling density near the center. It improves the reconstruction conditioning and SNR, which enables increased spatial resolution with a single shot. And the single shot acquisition improves the face robustness, which is essentially important under high B value. Romer EPTI preserves the image geometry to address eddy current-induced distortion across different diffusion directions. Therefore, it does not rely on post-hoc corrections. The EPTI without eddy correction shows substantial eddy current-induced dynamic distortions and depend on the eddy correction in post-processing to improve the geometry, especially at high B value like B6000 shown here. It's challenging to correct for those dynamic distortions. In comparison, Romer EPTI shows consistent geometries across diffusion directions. Here are the results we collected on Connectome 2. It shows that the 1.5 isotropic multi-shell Romer EPTI data is with DWIs up to B6000. What I want to emphasize here is that the image quality remains high across all shells. The single direction images and the mean DWIs show both high SNR and clean geometry, even at the highest p values. Thanks to Dr. Felix Dernert, presented earlier, we got Sandy for this multi-shell data we acquired. Here we compare different scan durations from 1/4 of the scan to the full scan. The different Sandy parameters are shown here, and also comparing the maps from different scan times. The 26-minute acquisition gives the parameter maps that are already close to the full scan. This demonstrates that SNR efficient acquisition can help achieve robust microstructural measurement at higher spatial resolution within a relatively short scan time. Here we show that with the variable density encoding, we can achieve higher spatial resolution within a single shot EPTI acquisition. Here shows the image at different resolutions from 1.5 millimeter to 0.88 millimeter ISO. At 0.88 millimeter, the images preserve high image quality without noticeable artifacts and show high SNR across diffusion directions. By going on to higher resolution with preserved SNR acquired within a short scan time, we can investigate finer structures for microstructure imaging and tractography. Here is an example of the multi-shell data acquired at 0.88 millimeter isotropic resolution. The multi-shell data acquired within 28 minutes, including 96 directions at B1000 and 2000, show high SNR and image quality in the mean DWI and colored FA maps. In the future, we will further apply more microstructure modeling at sub-millimeter resolutions. Romer with single-shot EPTI provides distortion-free, high SNR multi-shell data at high B and high resolution for microstructure imaging. We verified its robust performance on the ultra-high gradient performance scanner Connectome 2. The high-quality improved resolution and SNR from this acquisition can facilitate future translation of microstructure imaging. Thank you for listening, and I'll pass to Kaibo, my colleague.
Hi, thanks Susie for the invitation, and thanks Mingxiao for the introduction. My name is Kaibo. I'm from Boston University and the Martinos Center. And I will present our latest work on rapid multi-shell mesoscale diffusion MRI using accelerated Romer EPTI with joint execute attention network constrained reconstruction. We just heard from Mingxiao about Romer EPTI for microstructure imaging. And in this work, we're taking Romer EPTI to the high resolution regime, which makes it relevant for the study of superficial white matter, tractography, among many other applications. In vivo mesoscale diffusion MRI has been challenging, mainly due to the inherent SNR limit, more pronounced image distortion and blurring, and sensitivity motion at higher resolutions. Romer EPTI addresses these challenges by providing an SNR-efficient, distortion-free, motion-robust acquisition, which enables in vivo mesoscale diffusion MRI at 500 micron isotropic resolution at both 3T and 7T for the very first time. In this work, we present the joint execute attention network accelerated Romer EPTI for rapid multi-shell mesoscale diffusion MRI. By combining an interleave subsampling strategy with joint reconstruction, we're able to explicitly exploit spatial and Q-space redundancy through a pre-learned denoiser to boost the SNR and achieve high acceleration factor. We perform extensive characterization and evaluation on both simulated and in vivo data. And we demonstrate up to 6-fold acceleration for rapid multi-shell mesoscale distortion-free in vivo diffusion MRI with 72 directions spanning 2 non-zero B values at 500 micron isotropic resolution in 15 minutes. Conventional Romer EPTI integrates an SNR efficient and motion robust thick slice acquisition with rotating view encoding along the slice selection and readout dimension, combined with distortion-free EPTI encoding along the phase encoding and TE dimension. Following acquisition, super resolution reconstruction is performed to recover the high resolution volumes for each diffusion direction independently. Romer's rotating view encoding is inherently suitable for KQ undersampling. Therefore, in this work, to achieve high acceleration, we employ a complementary subsampling strategy for Romer's rotating view encoding to leverage the KQ data redundancy across Romer encoding and diffusion directions. Following acquisition, we perform joint reconstruction based on plug-and-play ADMM across all diffusion directions, subject to the constraint of a pre-learned joint execute attention network, which is a patch-based denoiser. We explicitly incorporate location awareness into the joint execute attention network such that the network is able to adapt to the spatially varying levels of execute redundancy. On the next slide, I will describe the joint execute attention network in more details. The joint execute attention network with enhanced location awareness performs denoising in a patch-based fashion. It is trained to predict the denoised Q-space signal at the center voxel given the noisy Q-space signal in its spatial neighborhood. It does so by performing spatially and Q-space adaptive filtering. To accommodate multi-shell data, we normalize the input image patch for distinct B values independently. Finally, in order to further enhance the network's ability to adapt to the spatially varying levels of spatial and Q-space redundancy, we explicitly incorporate location-specific information through feature-wise linear modulation, also known as film. Here, location-specific information is captured by the spatial correlation of diffusion-weighted signals. For example, in white matter, the diffusion-weighted signals are more homogeneous within the image patch since the directionalities are more consistent, whereas in air and in the CSF, the diffusion-weighted signals are spatially less correlated with each other. The network is trained on simulated data at 760 micron isotropic resolution in a fully supervised fashion. By performing denoising in a patch-based fashion, the network generalizes well to different spatial resolutions and also across different scanners. Once the joint execute attention network is properly trained, we use it as a plug-and-play prior through plug-and-play ADMM. Using simulated data, we optimize the proposed reconstruction through grid search over training noise level and ADMM parameter rho. We showed that the performance of the proposed reconstruction is quite stable and insensitive to the training noise level and rho within a reasonable range. Looking at the reconstruction RMSE across iterations, we demonstrate that the proposed reconstruction achieves fixed point convergence. Finally, we show that compared to conventional reconstruction, including joint reconstruction using locally low rank regularization, the proposed method achieves lower RMSE and much lower relative bias across different SNR values. Next, I will show the in vivo results. We perform in vivo experiment for single-shell diffusion MRI at 500 micron isotropic resolution with accelerated Romer EPTI on a 3T clinical scanner. In this case, we treat the fully sampled Romer EPTI data denoised by MPPCA as the reference. Again, we demonstrate that on the realistic SNR level, the proposed reconstruction offers low RMSE. With the same data, we demonstrate the reproducibility of DTI parameters at 4-fold acceleration. On the right, we plot the FA and MD values derived from 4-fold accelerated Romer EPTI reconstructed with locally low rank, the proposed method without and with film against the reference fully sampled Romer EPTI. We demonstrate that by explicitly incorporating location-specific information through film, we're able to achieve better reproducibility of DTI parameters. We then perform additional in vivo experiment for multi-shell diffusion MRI at 500 micron isotropic resolution on Connectome 2, leveraging its high performance gradient to acquire a multi-shell diffusion dataset at the mesoscale resolution with shorter TE and improved SNR. In particular, with the proposed reconstruction, we demonstrate up to 6-fold accelerated Romer EPTI, which reduces the scan time from more than 90 minutes to around 15 minutes for multi-shell diffusion MRI with 72 directions across 2 non-zero B values. Finally, using the same fully sampled Romer EPTI data acquired on Connectome 2, we characterize the flexibility of Romer's rotating view encoding and the proposed joint reconstruction. To achieve the same overall acceleration factor of 6, one can combine different number of diffusion directions with different acceleration factors per direction. We show here that different combinations of the diffusion directions and acceleration per direction results in similar quantitative maps, although more diffusion directions still leads to slightly less noisy maps. To summarize, in this work, we combine an interleaf subsampling strategy of Romer's rotating view encoding with joint XQ attention network constrained reconstruction. This allows us to achieve up to 4-fold acceleration on 3T clinical scanner for a single shell mesoscale diffusion MRI and up to 6-fold acceleration on Connectome 2 for multi-shell mesoscale diffusion MRI. The proposed method shows robust performance across different SNR levels. We also demonstrate that the proposed method works on both single shell and multi-shell data and generalizes well to data acquired on both clinical scanner and Connectome 2. And in the future, we will further develop and extend the proposed method to higher B values for microstructure imaging. Thank you.